Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. The third lecture, we're going to start talking about some more image processing techniques. So basically, we're going to start up with basically another type of images that is called DICOM images, DICOM image format, which is very popular in medical imaging modalities. And basically, it has a different kind of application or a reading function in Matlab that deals with it. Okay, so basically in DICOM format, you can actually store images of different dimensions, of different types. You can actually store even volumes inside the same one image file. You can also include some what's called metadata, as we're going to see. So basically, this is one very important DICOM. The DICOM image format is a very important topic to basically get familiar with. We're going to do some experiments with dealing with basically how to read DICOM images using samples from Matlab built-in images. And I gave you one sample image in the data that I posted on Blackboard. So we're going to see the difference between the two. We're going to see something based on what we read from the DICOM here. In the CT images in particular, we'll find that the range of images is really large. And basically, there is a very well-known technique in CT image display that's called windowing. We're going to explore that together so that we can actually display the CT images properly and basically focus on either bone, soft tissue, or basically if you have something that has air such as the lungs, we can also basically focus the display on that. This is a subtopic of something called contrast enhancement. So basically, contrast enhancement basically is one of these topics that basically deals with windowing. Window is one type of contrast enhancement. Here we're going to talk about more general contrast enhancement techniques, and they are based on something called histogram adjustment or histogram equalization. We're going to see some examples, and basically this is a very important topic so that you can improve the quality of medical images that you have. Then we're going to start talking about basic filters, image filters. We're going to deal with two types, linear filters and nonlinear filters. They are very important. They are used heavily in medical images. You need to know the theory and the applications of each. In order for us to test the filters that we have, we're going to learn how to simulate some noisy images so that we can actually test the filters on them and basically make sure that the filtration was effective. The problem without simulation is that when you have an image with noise, you have no way of telling whether after the filter, whether it became better or worse, because you don't have a reference. Okay, you don't have the reference image without the noise. You can basically tell that qualitatively, but quantitatively it's very difficult. So basically, simulation is used to study the effectiveness or the performance of different filters. We're going to do some basically experiments with what's called image filters. And basically, image filters, you design the filter using something called F special and then apply the filter using image filters. For the nonlinear techniques, you have several what's called morphological operators, and basically you can use these with a design that's called a structuring element design, and basically these together will basically allow you to do experiments in linear filtering and nonlinear filtering. Okay, so let's get started. So basically we're going to go to Matlab and basically get started with, can you all see Matlab? Can you all see Matlab?
Yeah, we can see.
Okay, so basically I'm going to start with images that are in Matlab built-in functions. I think they are in C. So Matlab, the same folder that we used last time, toolbox, images, and then image data. Okay, We saw this folder last time. Let's pick a DICOM image. Let's see if there is a DICOM here. Usual DICOM images appear like this. Basically, they cannot be read. Here you have ni1.dcm and ni2.dcm. Okay, so the function that reads DICOM in Matlab is DICOM read. It's very easy actually to basically go to here, for example. Maybe you can just search here in Google, just say Matlab DICOM. That's it. Okay, you'll find here the reference for DICOM read. Okay, so the DICOM read, all you have to do is just put the file name there, and basically you're gonna get the image on the other side. Okay, there's another interesting function actually that we're going to use also. If you go to the C also, I think there's a function called DICOM info. Okay, so the DICOM info basically reads the metadata that is basically inside the DICOM file along with the image. So basically, one function reads the image, the other one reads the info. And the info, as you're going to see, actually has extensive amount of information. So for example, if you're using MRI to do your scanning for the image, for example, you're going to see the manufacturer here, GE Medical Systems, for example. You're going to see exactly the study. Okay, usually on the interface for the MRI image, you have a study description and you have a sequence name. So basically, you're going to see also the sequence name. You're going to have all the information basically. And you're going to have the size of the image, rows and columns. You have the number of bits for each one, for each pixel. So basically, you're going to have an extensive amount of information. Okay, let's try that. So now basically based on the image data here, the file name is ni1.dcm and ni2.dcm. Let's try them. So basically you're going to start first of all with DICOM image reading. Okay, so I'm going to say image equals to DICOM read of ni1.dcm. DCM is the extension for DICOM. DICOM images are images, but they cannot be read by image read like what we did last time. So basically, we have to use DICOM read. Okay. So after we read that, all we have to do is basically just display it. So figure 1 and image show of image, and that's it. Okay. And let's also do the DICOM info. DICOM info of the same file name. So the first function reads the image, the second function reads the info. So let's run that. Okay, doesn't look very good, huh? Actually, this is one of the things that I wanted you to notice. Basically, the scale that we have, basically when we read the DICOM info actually wasn't working because we have to remove that semicolon in order for that basically the output to come out. So I'm going to try that again. So this is the DICOM info, okay? As you see here, the number of bits is 16. And the meaning of 16 bits is that the numbers or the grayscale is from 0 to what? To 4095, okay? So basically 2 to the power 16, okay? So 2 to the power 16 actually is 2 to the power 6. Actually, it's more than that. It's basically 2 to the power 16 minus 1. It's actually 65,000, okay? So the problem with that is that basically the image data will be basically spanning from 0 to over 60,000, while the display will be basically just from 0 to 255. And this is a problem, basically. You cannot actually display, if you try to display something that is much larger than the capabilities of the display, you're going to get something that looks like what we saw here. It looks very bad. So let's try now to use image scale. Image scale actually scales the image before it displays it, okay? We started seeing something, but it's in color, like what we saw last time, okay? So all we have to do is just say color map, Great, if you remember. So now we can see the image. Okay. Let's add these two steps basically into the here. So instead of just having the image show, we're going to have image SC of image and then color map of gray. So that when we run the file, when we run this code, we're basically going to get a correct display of the knee. This is basically a cross section of the knee. In the information that we saw here, this seems like a cross-sectional image in the knee itself. Okay, so basically here you're going to find all the information, not just about the way the sequence or the manufacturer of the machine that was used to do that. Basically, you have here MRI. The manufacturer is ONI. You have basically this is a right knee. Okay, and basically you have the, of course, some of the data might not be there because basically since this image was posted in a database, a public database, for the privacy for the patient, they usually remove all the patient info. Actually, when you look at the DICOM image in the hospital, you're going to find basically all the information of the patient right there. Basically, the MRI acquisition type was two-dimensional. The sequence name is fast spin echo. One of the very well-known techniques in MRI, if you studied MRI, is fast spin echo. And the slice thickness is 3 millimeters. Repetition time, TR, is 3.25 seconds, or 3,250 milliseconds. The echo time is 27 milliseconds. So basically, all the information you need about the image, how the image was acquired, is contained within that DICOM image. This is extremely convenient. Think about telemedicine, for example, teleradiology. In teleradiology, you send the image to the doctor somewhere in order for him to be able to make a diagnosis. In order for him to make a diagnosis, sometimes it's very important to have not just the image, to have the information about the image, how the image was acquired. Otherwise, it's a big problem, actually. It's basically, he might not exactly know what's going on, okay? So basically, imagine that a lady was doing a mammography, okay? It's very important to know whether this is the left or right breast, okay, for example. And it's usually very important when you have an abdominal image to know exactly the orientation of the slice that you're talking about in order for you to be able to determine exactly what's wrong with the image, okay? So it's very important. Basically, the information is contained within the same file. It's just one file, as we saw here. Just one file, just one file. And this one file has all the information, including the image and including the patient information, and including also the all the technical information that basically represent the way the image was acquired. Okay, so do you have any questions about the DICOM images?
Did it only contain 2D image, or it can be also 3D in one file, doctor?
Yes, it can be 3D in one file. Yes, yes, definitely. And actually, it's very common actually to send the images in just one file like this, even if it's 3D. Any other questions?
Doctor, only when we want to display the image and the information related to this image, only we use image scale?
Image scale, when you display the image, when you want to display the image in the correct format, usually you'd like to do that. This is an image that comes from MRI, and basically from the DICOM info, you saw that each pixel is represented in 16 bits. Okay, so since it's represented in 16 bits, it means that usually if you want to display the image correctly on the screen using image show, IM show, you have to have the image between 0 and 255 or 8 bits. If you have the scale of the image or the range of the image, basically you have much higher quantization, number of bits, then you would need to have image scale in order for you to be able to adjust the range of the image to the range of the display.
But my question is the information, what you read from about 2D MRI, this information, how can I display it?
Just DICOM info.
DICOM info. Thanks a lot, Doctor.
You can do it before you read the image, by the way. You can do it before. Maybe you can just basically you comment out all these, okay, and basically clear this TLC, okay, and basically run it again, run the same code again. You're going to find the same information. So basically, you can start with reading the info first, and then decide how you're going to display the image and or so on. Okay.
Thanks.
Okay. So this is 16 bits. Okay. There is one function that you can actually use to see exactly what's going on in the image. Basically, we can instead of just looking at the image itself, we can actually look at the histogram of how the images are basically represented in terms of values. The histogram is basically a display of the values of each value of the image and how many pixels were actually given that value. Okay, let me show it to you right now. Okay, let me just discuss it with you first on journal, and then. So basically, I'm going to talk about histogram. Histogram is general, by the way. It can be for anything. It can be for 1D signal, 2D signal, or 3D signal. So basically, the histogram is just a display of something that looks like this. You basically have, on one side, you have the pixel value, and here you have the number of pixels. Meaning that if you have a certain value for the pixel, for example, 100, if this comes to be somewhere here, for example, if the value is a number here, okay, then basically it tells you that this number here, if this number is, for example, 1000, then it means that 1000 points in the image have a value of 100. Okay, so basically you display that so that you know exactly how the images, how the different ranges, or basically how the distribution of values within the image look like. Okay. Let me try and basically show it to you here. Also, we can actually find the function Matlab that does histogram, but actually let's go and because actually we need to learn how to search for information. So basically you gotta go back. Sorry. Matlab histogram. Maybe you can put also image. Histogram of image data. It's right there. Okay. Please, when you're trying to do something with Matlab, please do it the way I show you here, okay? Because actually it makes it easier for you to learn new things, okay? And you will never remember all the names of the functions. You probably need an image histogram function now, but probably the next time you need it, it's gonna be probably in a month, after a month. You're never gonna remember the name of the function. So basically, this is an easier way to do that. This is basically, at least this is what I do, because I never remember the names of the functions. So it's just image hists, okay? Let's try that. Just image hist is basically going to display something that looks like this, okay? This is a range, this is the values. Basically, this is an 8-bit image, so it's from 0 to 255. And here you have the number of pixels having these values. So for example, if I take this point right there, basically it's about 1200, okay? This grayscale or this gray level has this 1200 points in the image, okay? Let's try it with the image that we got now. Let's uncomment that. Basically, you can say just image hits, and maybe you can draw it in a different figure so that we can see the image and the histogram at the same time. So basically, image hist of image. That's it. Let's try it. Okay. it looks a bit strange actually. It's this is 10,000 2 to the power 14, but actually most of the images are there. So let's try to magnify that a little bit here. See here, everything is very low, in the very low grayscale. Let's try to magnify it. Let's just choose zoom in. We can just do it like that, basically. Actually, it kind of looks very strange. Actually, it shouldn't really look like this. It should actually have many more values actually in the other side here. I'm not sure why. Okay, because it has so many black points. The black points actually are dominating the image itself. So let's do something a little bit so that we can see the other part. Maybe you can just say zoom in. Basically, I'm going to take the values after the 0 so that I can see them in a much better way. Okay, let's go back to the original scale. Okay, let's so focusing on the negative part. Okay, better display it again. It's easier to display it again. Okay, it's right there. I'm going to take the values after these very high values. So basically, I'm going to do the same tool, use the same tool, zoom in, and basically take the whole range here and zoom it in. Actually, I still don't see it. Okay, I'm not really sure. Maybe maybe the number of points, the number of points in the histogram are not sufficient. So basically, there is another point here in the histogram. Another entry here is n. How many n? How many bins? Basically, you're going to have for your histogram. So basically, instead of just having very few bins, bins meaning that if you look at this figure here, basically, you're not going to display for each point. Basically, you're going to display for ranges. So basically, you take this and this. Basically, consider each one of these as a bin. It's bin like it's, you say, for example, trash bin. Trash bin is basically a small box where you actually accumulate things. Okay, so for a bin, basically, you take the whole range. For example, if you have the range from here to here, okay, and basically you divide it into different bins. So that when you're talking about the value here, it's going to be from this one to this one. The value here is from this one, and so on. Okay, so it's easy to do it this way because sometimes some values do not really get represented at all actually inside the image. So basically, if I do the same thing again, and just do image hist of image and basically divide it into 100 bins. Let's see if it became better. Actually, I don't see any difference.
Doctor, maybe you can histogram function, not mhist.
Histogram? Okay, actually, image hist, it should be okay, actually. But let me, first of all, let me just get the minimum maximum of the image. Histogram actually gives you the actual histogram. The minimum is 0, and let's see the maximum. Maximum is 400. Okay, okay. It's very small actually. It's a very small number here. So because it's a very small number, the number of bins that we have, even if it's a 100, basically it's 100 bins. Actually, it's not gonna do anything to the range that you have here. It's basically what we need to do is either multiply this by a number so that it becomes larger, basically relative to the actual size of the image at 16 bits, or basically make the size of each one of the pixels smaller so that we can actually basically have this relative to the actual size a little bit more considerable. So basically, I'm just going to try the other one. So if I multiply this by 100, okay, this makes the range of the image between 0 and 47,300. Okay, so if I do it this way, oh, sorry, not this one, the image hist, and we can keep it, no, it doesn't matter actually. Just multiply this by 100 here. Figure 1. See now? You see now the histogram. The problem before was that the maximum range that we have is the 2 to the power 16. 2 to the power 16, all the values of the grayscale that we had are between 0 and 2 to the power, basically 512 is about 8, to the power 8, to the power 9, okay? So basically we had most of the images, most of the image data, or most of the image values in a very small portion of the whole scale, okay? So you had, basically the scale was about maybe 7 to the power 7, which is about 128. So basically the range of the image data was 1 over 128 of the whole range. Okay, so basically if you see it like this, basically you can see, basically if you have different structures, you have the distribution, you can actually see where most of the pixels are, and basically you can adjust the image intensity based on that. Okay, so basically one of the ways that we do actually to deal with an image that looks like this, basically if we use image show that like what we did in here, basically it used something called contrast enhancement. Contrast enhancement will basically take the original image and basically adjust the intensity so that it can display properly on the display. Let me show you a more extreme example of that. When we read the image that I gave you, one of the images that I gave you was basically a CT image. If you remember, one of the things that were in the file that I put for you on Blackboard, I think its name was, I think it was CT 00043 DCM. Let me show you this particular example because actually it's very extreme. So image 2 is equal to DICOM read of this, okay? Okay, and basically let's display here just to see what's going on in each one of these, minimum of image and maximum of image, so that we know exactly how the ranges are for each one of these. And I'm going to display it also using the same thing because actually it has the same problem. This will have something very unique. We'll show it in a second. Okay. Let's forget about the histogram for now, because I'm going to show you another way of seeing that and dealing with that that is much more elaborate. So basically in figure 2 now, we're going to see the other image, image 2. Okay. Okay. Okay, there's a missing, this maximum is this. Oh, okay. Okay. The same thing, okay, sorry. Forgot to correct it in both. Okay, so now this is the CT image. Okay, this is the knee image that we just saw. So, okay, this is an MRI image. This is a CT image. Okay, let's see the difference between the two. Here, the minimum, okay, I'm sorry, I forgot to change that to image 2 also, so that we see the range for image 2. Let's just take that and run it. Difference between the two, for MRI, it's an absolute image. You will never get a minus value or a negative value in an MRI image. For CT, if you remember from your medical imaging course, CT numbers are absolute, meaning that not absolute. Basically, they are not. They are real numbers. They represent something in the image itself. They are basically relative. The relative difference or the relative percentage difference between the attenuation of that part of the image to water. Okay, so basically, if you have something that is thicker than water, that has more density than water, like bone, for example, it's going to be positive. If you have something like air, where it's much lower than water, then you're going to get a negative number. So the values for CT are usually -1, -1024, which is basically for air, okay? And it can go up all the way to 3,000, 4,000, depending on the material that you have inside the body. So if you have a bone, then you'll end up having like 2,000, 3,000, something like that. If you have a metal, for example, if someone has a metal plate in his knee, in his skull, something like that, then you're going to go even much higher than that. Okay, so if you display also, if you try to display the CT image with image show assumes that you have an image between 0 and 255. It doesn't assume that you have values beyond that. So basically, if you take this image and try to display it using image show, basically you're going to get something that looks like this, very hazy. You're not going to see much in it. Okay, so there is a much nicer tool in order for you to adjust the image for display called image tool. Image tool, yes. Image tool. So basically, if you have an image like image 2 and you run image tool, you're going to get the same image here, but actually you can adjust the contrast. This is actually not just a display window. This is actually basically an application within Matlab. So basically, if I wanted to adjust the contrast, I can do that from here. I can see now the range of grayscale, and I can see the histogram. I can focus on each one of these, whatever part I want to focus on, and basically see that part. So here I'm focusing on basically soft tissue. If I move that to here, all the way up, I can see only bone, okay? So basically for CT in particular, not just any modality, just for the CT, the numbers that you have in your image are called CT numbers. Maybe you can write that down. Basically, this is just unique for CT images. You have CT numbers. They are basically equal to mu minus mu water over mu water times 1,000. Okay, it means that if you have water, the value will be what? Basically, this is going to be mu water. Okay, mu water minus mu water is going to be what?
Zero.
If you have air, how much is the attenuation of air? Almost zero. Okay, for radiation, it's almost zero. So basically, you have here 0 minus mu water over mu water. So it's going to be what? Almost minus 1,000. If you have bone or any other tissue that looks like bone, you're going to be basically the attenuation will be definitely more than water. So basically, you can get a positive number somehow. And usually, you can go all the way. If you have bone, you can go all the way up to 3,000 or something like that. Okay, or more if you have metal plates. So you have now a problem of displaying, how to display this. And the way they do it, this is actually the way the doctors look at these images, because basically these images not just have all the values of the attenuations, usually it's very difficult to look at the different tissue types at the same time. So usually the doctor likes to see something called water window or an air window or a bone window, meaning that he's going to focus on only one of these. Okay, so if you're talking about water, you're talking about soft tissues, because soft tissues are very much like water or around water. Okay, they are very much like water. Okay, so basically, this is like a soft tissue window, this is like an air window, this is like a bone window, and basically from the same image you can get 2 different or 3 different images that look very different, but actually they represent different components of tissues inside that image. So instead of like for example in MRI, if you want to look at different things, you usually have to run different sequences to get different images. For CT, you can get one image, and you can basically, using the way you display the CT image, you can get basically different images based on that. Okay, so the way you do it is very simple. The way it's practically done. Basically, you have the display range, basically, from here, say, to here, okay? And you have the actual image ranges from here to here, okay? Okay, basically this is from 0 to 255. This can be from negative 1000, say 3000, okay, for example. You cannot do this mapping. If you do this mapping, just literally, like what we saw, you know, basically, we can just do this, okay? If you just make it literal like this, basically, do this kind of scaling, okay? So make minus 1000, you make 0, and the 3000 make it 255, and scale everything, compress everything in that range to be within that range. If you do that, you're going to end up with an image that looks like the one that we just saw. Maybe I can just display it again. Image show. It looks like this, basically. Because basically most of the images, most of the data, the numbers in the image will be on the lower side. So basically you can see something that doesn't have any contrast, basically. The contrast is really very bad, actually, when you look at this image. We want to do something that make it look like, basically, the image that we just saw here. I can actually have, I will select a center here, I will select a window here, and basically move that, and basically see different images as I move. Okay, this is called the center here, the center line here is called the level, and basically the range between these two is called the window. Basically you can adjust this window you like. Okay, so basically what's going to happen, what happens here is that we take, instead of taking that, which is wrong, this is basically not the way it should be. What we're going to actually do is basically select a particular range that we are interested in, for example, from here to here. Okay, and basically this range here will be mapped from here to here. Only this range. And this range has 2 properties, actually. Basically, you have this property, this is the level, and you have this property, which is the window. And you can adjust both. Okay, so basically you can have something that starts from here to here, or start from here to here, but at the same time, in each one of these, basically, you're going to scale it all the way to the 255 range of the display. Okay, but this is actually, this is not done by calculation, this is done visually by the doctor. So the doctor on the screen, basically, if you saw, has anybody of you seen a workstation, a viewing workstation in a hospital? in the radiology department? Have you seen anything like that before? Okay, if you haven't seen that before, what usually you expect, basically you have an image that looks like this, you're not going to see something that looks like that, because the doctor will not basically understand the histogram and basically do the things that we do here. Basically, they allow the doctor to basically, whenever he moves horizontally, he increases the level. When he moves basically vertically, he controls the window. So basically, by moving horizontally or vertically, you can adjust this window and display the image properly. Okay, but actually what we do here, because actually we need to understand it a little bit better, we do it manually. We do it here based on the histogram. So basically, I adjust the window here, as you see, okay? And I adjust the level by basically taking everything here after I select the window size. And basically, if I stop here, and make it a little bit smaller, I can see only bone now. So I'm focusing on bone now, basically. I don't see any water, I don't see any air, everything but bone disappears from the image. So this can be very useful, or if you are interested in seeing the bone in the image. If you move the same level, if you change the level here, you start seeing the soft tissue. Soft tissue, as you see here, is the parts. Basically, you have here fat, you have here bone, you have here muscle, and the bone is still there. You cannot take the bone out. But what can happen is, if you go back to here, if I adjust this window to basically the display here, whatever comes outside, or basically everything here is 255, everything here is 0. So all these parts are 0. All these parts are 255. So the bone that you saw here, because it's higher than the intensity that we have, higher than the highest intensity. So all the pixels in the image, all these points here, from almost 1,000 to all the way to the maximum value, basically all of them will be represented by 255. If you go a little bit down, now you see a little bit more of soft tissue, okay? So basically you start seeing things that you didn't see before inside the lungs. But actually, if you go all the way, basically here, everything is above, so basically it doesn't make sense. But actually, let me make that a little bit smaller. Let us just focus on that one peak. Actually, that one peak is not very useful, actually. It's just the whole image. If I move it a little bit, see now? If you look at the original image, basically, you don't see anything. You don't have any contrast. Here, you adjusted the contrast so that you see the parts inside the lungs in a much better way than what you would see if you increase it all the way up to have the whole intense image in the window. So here, this is the display that we have for this particular image. And basically, you see some vessels here, but not many vessels. If you focus on the vessels here, you see so many of them. And this is very important, because basically this part here became very clear. It seems like there is something wrong here. This is like a nodule, lung nodule here that should be detected. When you have it basically inside the whole range like this, okay, sometimes it can be confused by something else. It's not probably as clear as when you have it basically in an air window display of the CT image. Okay, so basically the one way of doing contrast enhancement or contrast adjustment. The contrast is basically the way you display the image so that it becomes clearer to the viewer. Okay, you're not changing anything, you're just changing the way the image is displayed. Okay, is that clear? So for the windowing technique in CT in particular, all you have to do is just select a level, a center, and a window, a range of grayscale values that you display into the range of the display that you're using. Is that clear? This is unique for CT, by the way. This is very unique to CT. Okay? I'll show you the same thing actually when we, instead of opening here a CT image, we're going to open the MRI image, for example, that we saw before, okay? And see what's going to happen or what we're going to see in the MRI image, okay? So basically, do that here, image tool here of image. This would be for the MRI image that we read from the built-in images in Matlab. It's right there, okay? So basically, this is the image tool. In order for me to get into the contrast enhancement or the adjustment of the contrast is here, okay? This is just a comment, it doesn't matter actually. Now you see the grayscale here. Actually, the grayscale is, as we saw before, it's the maximum is 473. So basically, this is the whole range from 0 to 473. It doesn't have negative numbers. That's it. If you adjust it, basically, it's going to give you something that doesn't make sense. Basically, see now, this is not representative of anything. By the way, if I move it to get that other one, it's the same thing. It's basically it's combining things that are different. These are bones. These are, I think, they are either ligaments or cartilages. They are not the same, basically. So it's very rarely when people actually use such adjustment for MRI. But sometimes, if the doctor wants to see something in a little bit different color or a different display technique or something like that, sometimes they do that. But usually, the original image is good enough. Okay. The only thing that we do basically here, see here now that this is the full range. When I make it a little bit smaller, sometimes it makes the image a little bit brighter. Okay, so this brightness might help the doctor see things a little bit better. But sometimes you can do that. But this you don't have to do it with a window and a level. Okay, you can do it actually with something that is much easier called image adjust. There is another technique also that we can use. It's called histogram equalization. These are two techniques that you can just directly apply on the image, and basically the image is guaranteed to come out exactly the way you want it. Let me just give you why we should use these functions instead of doing that here manually. Basically, if you ask the doctor to do that manually each time, if you have just a range like this, and you have very, very small, very few pixels in the remaining range here, basically, it's going to be really tedious because sometimes each study might have like 200 images. So it doesn't want to have that, doesn't want to do that for each one of these images. You want to just apply a certain technique and basically all the images come out nicely after the processing. So basically, there are techniques that you can use in order for you to be able to adjust the intensity of the pixels here so that they can better fit the display of your computer. Okay, so I think we should probably break now for prayers, and when we come back, we're gonna discuss how to adjust the image intensity, how to do something called histogram equalization, and both of these techniques target making the contrast of the image better. Okay, and then get started on talking about the image filters. Okay. So we're going to take a break and basically let's get started at 7:10. Would that be okay?
Okay.
Okay, I have one question. I have one question before we leave. There is a problem on next lecture. We cannot have a lecture on National Day. Okay, that's a problem. It's not going to be allowed. Basically, okay. So basically, next Wednesday, you cannot have a lecture. So I decided to do something a little bit different. I'm going to give you an assignment set so that you can apply all the techniques that you saw so far in this assignment and basically deliver it by the following week. And regarding the lecture itself, you can either cancel, okay, or postpone, or basically change time, basically, and change day. You have to change day. Basically, this is going to happen anyway, okay? I'm going to give you an assignment so that you can basically get started on things, and I don't want you to listen to a lecture, several lectures, and basically after a month or so, you're going to have to deliver a certain report, and basically you haven't started yet. Okay, so this assignment will help you get started. Okay.
Please, Doctor. Regarding to the research problem number 1, the deadline is 26.
No, it's not. I'm gonna change that. Don't worry about it. Okay.
Okay,
So this is not RP1, not RP1. This is a different assignment that I'm going to put. This is a practical assignment. I'm just gonna give you a few problems that you have to solve with Matlab. Okay. So for example, I'm going to give you a very small image. I'll tell you to magnify by 32 times. Okay. For example, things like that. Give you an image and tell you to a basic DICOM image, tell you to give me the name of the manufacturer of the machine that was used, for example, okay? Things of that sort, okay? So this is gonna be like a small problem-based assignment. It's gonna be very simple. If you want, because actually I don't want people to have to work during the holiday because it's a long holiday. Some people like to maybe travel during that holiday. So I would prefer if you cancel it, but actually if you want to change the date to either Tuesday or maybe Saturday or Sunday next week, the following week, it's going to be fine with me. But actually, if you're okay with canceling, it's going to be fine with me also. So what do you prefer? Because we cannot have a lecture on the National Day. This is exactly on the National Day. So basically, we have no excuse to have a lecture on that day. So, and basically, the university will not like that. So should we go ahead and cancel? Okay, if you want to think about it, we can talk about it after the break so that we can catch the prayers, okay? Okay?
Okay, doctor.
Okay. So I see you after the prayer, inshallah.
Inshallah.
Assalamu alaikum.
Wa alaikum salam.
Now we're going to go back and try image adjust. Basically, do you have any opinion about this? Should we just cancel the next lecture or on Wednesday, or you want to have it on Tuesday or maybe Saturday or Sunday? What do you think?
Lecture, if you don't mind, we would like to cancel the lecture. We would like to practice more on what we have learned before.
That's fine. That's fine. That's why assignment is basically going to be very useful in this. Okay, that's fine. This is what we're going to do, inshallah. Okay.
Actually, I have a question.
Go ahead. Go ahead.
The contrast when the patient does the MRI image with the contrast dye. Does it help with the? Does the contrast dye help to enhance the image?
Actually, the contrast is usually for MRI in particular. You use it for vascular imaging. Usually, you don't really use it for tissue imaging. Okay, so the main advantage of using a contrast agent in vascular imaging is that you get the images with higher intensity. What happens is that basically you're taking so many different images at very short intervals, and unless the magnetization of each one of them returns back to its original value, the images will be fading away. You know, the longer the sequence you have, the images will be fading away, and basically you're not going to be able to discriminate between the blood vessels and the surrounding tissues. Okay, so basically the contrast basically reduces the T1 of the blood in the blood vessels so that it recovers faster, and since it would recover faster, you're going to be able to see it much more clearly. They'll be much brighter, while the surrounding tissues will be still basically very low in level, so you can discriminate between them. But you usually don't use MRI contrast agents for tissues, for the actual soft tissues. Okay. So now we're going to talk about basically the topic we're going to talk about is basically contrast adjustment. A contrast enhancement. Okay, like what we saw before, basically when you have something that looks like this, basically you're gonna get an image that looks like this, basically. Not like this, the other one. Yes, this one here, I think. So basically, when you change that level here, you see something that looks a little bit dimmer. It's not bright as it used to be before. So basically, the best way to display the image is to see the histogram and basically adjust the starting point and the end point of the display basically between the significant parts of the histogram. Okay? So what we're going to see now are basically automatic techniques in Matlab that allow us to do that. We're going to try with something called first image adjust. And then there is another function called histogram equalization. Okay, image adjust, basically what it does is if you have a histogram that looks like, for example, if this is the range basically that you're talking about, if the histogram looks like this, it's going to adjust this histogram to look something that looks like this. It's going to basically expand the part where most of the pixels are so that it covers the whole range of the display. Okay? For the histogram equalization, basically it tries to do something a little bit different. It wants to take this and make it almost flat. It wants to basically take all these values and try to equalize the histogram. Equalize meaning that all of them almost the same, but you can never have them the same, by the way. But actually, it's going to basically try to change. This is actually a change. This actually does change of gray values, by the way. Okay, so basically this is will change the grayscale values here and basically expand that. But actually, when you look at it after expansion, it's going to be different from that. So this is one technique that basically just expands the range. So basically, it's going to be just a factor multiplied by the actual intensity. Here, it's a little bit more complicated than that. Let's try both and see what happens. So we're going to take one of the images, like for example, let's start with the MRI image. Okay. So let's display the, let's just say figure 3. And basically, I'm going to display the two images side by side, okay? Usually, it's one of the nice things that we can do, actually, if you have image show, you can put these two images side by side here so that they can fill out the whole image. So let me show it to you how it's done. Basically, let's just take, which one? Take image. And image adjust of image. And histogram equalization of image, the same image. Okay, so you have the original image, the basically the adjusted image, adjusted image, and the histogram equalized image. Basically, what I do here when I basically in Matlab, when I put all the images within brackets like this, I'm concatenating them. For example, okay? Basically, this will come out like one image. Okay, that actually looks nicer when you display it. You're not going to have borders. I'm going to show it to you. I'm going to show you another way of doing that using subplot. You'll find that this is a much better way than subplot, because subplot actually leaves spaces between the images. But this concatenates them. So basically, it takes this one here and puts the other one right by it, and the third one right by it. The most important thing is to have the same size for all of them. If one of them has a different size, you're not going to be able to do that. Okay, so let's try that first and then try the subplot and see which one is better. So now I'm going to display using image show the original image, the image adjusted image, and the histogram equalized image. If you remember, when we tried to do that here for the new image, it came out like black. Okay, it looked black. When we do the adjustment, we had to use image scale here. I'm not going to do image scale. I'm going to do image show, but with the image adjust and the histogram equalization. Let's try that. Okay. See now, this is the first image. Basically, it's exactly the same problem that we saw before. This is the image adjusted. This is the histogram equalized. Okay. For the histogram equalization, you will see that basically even the noise in the background, you can see it now. Okay, see the noise actually became very clear now. Here, actually it looks much better, but here you might see some details that are very difficult to see. Like, for example, the structure of the noise here is not really visible altogether here. But it's very clear also that this image here is very close. If you look at this one here, the one we adjusted, okay, is this the one? Maybe this is the one. No, not this one. This is not the one. This is the new one, actually. So let's get the old one. Not this one here. Okay. See, basically, if you take the whole range, let's just display them side by side. Let's close this one. See now, this is not actually this one. This is not taking everything. It's basically adjusting the image to the end of the useful range of the histogram. Okay, so basically this is this here, not this. Okay, even though this is okay also, this is actually not bad, but actually this is better because basically you're making the whole range of the display actually more useful. When you see an image that looks like this, you see everything in more detail, or basically the contrast between the different grayscale levels is much better than compressing and having a slightly dimmer version of it, like in the one here. Okay, so this is actually very good. So image actually does a very good job. For this one here, we're not sure really what happened actually. Let us look at the histogram and basically compare the two histograms. Okay, in order for us to do that, I'm going to display them in, maybe I can do it here so that we can keep it bigger. For subplot. Let me try first of all the subplot first and show you the way subplot displays the images, and then we're going to use it to display the histograms. 1, 3, and 1. This is an array of 1 times 3. It's one row and 3 columns, and I'm going to just have image show of image. And then I'm going to repeat that for image adjust of image, and histogram equalization of image. And basically, I'm going to put this in the second position, this is the third position. Let's run that and see the outcome from. See now the difference between these two. This is the one using subplot. This is the one using image show with concatenation of images. Do you see the difference? Even if I magnify this, actually the images will look very small compared to the background here. Here, I'm utilizing the whole area, as you see. You see the images in a much larger way. See the difference between these two? So I would prefer if you use the way I showed you now so that you can get the images basically clearer when you try to look at them. Okay? Okay, let's close the image tools, because actually they are, one of the things about image tools is that they don't close by themselves. Okay, so you have to close them one by one. So if you have a code that has image tool, after you finish, you have to basically, if you run the code several times, you'll find as many image tool windows on your screen as the times you ran your program. So basically here the image tool, I'm gonna comment it out because actually you don't wanna have it running. And basically instead of having that here, I'm going to have the histogram. Instead of image, I'm just gonna put image hist. Okay to keep them in subplot because basically we're just going to see the shape of the histogram. Okay, how do you like that? See the difference now between the histogram equalization and the image adjustment. Let's look at the range. Basically here the range is exactly the same, but actually what the histogram equalization did was try to basically make the grayscale levels having exactly the same number of points. So it modified the grayscale values inside the image. If you look at the image again, actually this is different because here, as you see, instead of having the noise at 0 or near 0, now you have the noise, the lowest grayscale in the image at around 2 to the power 10 to the power 4. So basically it's about 20,000. Okay, so instead of having the noise near 0, now you have the noise levels at 20,000. Okay, which is actually it's much higher than what it should be. Okay, that's why all the details in the background basically they are now represented, instead of representing by black, they are represented by gray. So you see the different parts of the image with noisy appearance. That the noisy appearance becomes clear because the small differences that were close here became very large here in the histogram equalization. Basically, these are techniques. We saw now 3 techniques for contrast enhancement or contrast adjustment. Let's call it contrast adjustment. Basically, in contrast adjustment, there is no best way, basically. You have to try different things. And basically, based on the outcome that suits your application or whatever, if you're working with a doctor or something like that, whatever the doctor wants basically is the best for this particular application. Okay, the two methods that we saw, that the automatic methods are image adjust and histogram equalization. Okay, the manual method that we saw is image tool. Image tool basically displays the histogram and lets you play with the histogram so that you can actually basically look at the image the way you like it. Okay, and if you look at how it works, image tool, you can actually, after you adjust the image, you can actually save it the new way, so that you can basically keep it in the contrast enhanced version. Okay, go ahead. Go ahead if you have a question.
I want to ask you about how can I save the image after I enhanced after it's enhanced in the image by using image tool.
Okay, let's go back and do that. So we're gonna start with the same image here, image tool.
I want to ask you about how to save it. Not
Yes, you have to be inside the tool to be able to do that. Okay, so basically, I'm going to have the image. Basically, this is the adjusted image. For example, this is the adjusted image here. Okay, basically, what I do here, I can scale. I can apply that. Basically, I can basically adjust data, meaning that I can change the actual values that were in image and make them basically to match the new window and level that I chose. So if I say adjust data, basically it took whatever you adjusted and basically displayed that over the whole range. And now your image has the version that was adjusted by this program. Okay?
Okay, thanks.
Okay. So now you understand how I don't want you to get into the details of the theory of each one of these. These are the techniques that we talked about. Basically, these techniques are automatic. Let me write that down so that it can be clear. This is number one. This is number two. Both of these are automatic. And number three is image tool, which is manual. You do that manually. Okay. So image adjust takes the same shape of the histogram is maintained, but actually what happens that it expands the range of the histogram to match the range of the display. If you have the range of the display until this value here, and you have the histogram until this value here, so basically it expands things as if you're stretching the histogram to basically fill out the full dynamic range of the display. For the histogram equalization, is different. Basically, you're changing the histogram so that basically you have a flat histogram. If you want to know some more details about how histogram equalization works, let me give you an idea about that, because actually it's very interesting to know that. Okay, if I have, for example, an image that is 100 by 100. And this is actually the number of grayscale levels is 1000. Okay, so basically 1000 gray levels. Okay, so basically how many points here do you have? How many points do you have? 100 times 100, it's about 10,000 points, right? 10,000 points. Then if I wanted to have an equalized histogram, from 0 to 1000, for example, okay? Wanted to have it like a flat histogram like this. How much is the value? How much should this value be?
10.
10, right. Exactly 10, right. Why? Because actually you basically divided the number of points over the number of gray levels, and basically this came out like 10. So you want to have everything here like 10. Okay, if for example, what I had at the beginning was basically I had the first point here at 0 at 100. okay? And then I have another point here at, for example, 50, okay? At, for example, 10, okay? What's gonna happen is the following. I basically start with the first point as is, okay? The first point is 100. 100, basically I should have 100 here when? How many points should I have here? Basically, at which point here should I have 100 points? 100 points is basically the accumulation of that. How many points, or at what gray scale here, or what gray level here, should I have 100 points if I assume that I have the value for each one as 10? I should probably have here like 10, right? At 10, you probably have 10 values here times 10, then it's 100, okay? So what I do for histogram equalization is that I start here, the first point here is at 10, and I put the 100 at 10. Let me show it to you in the figure that we had. Here, look at this point here. This point is about 14,000 or even more than 14,000, okay? It started at what value? At about maybe 20,000, something like that, okay? The number of points here was divided, and basically the point here, the value here that was really high started from the point when actually you're expecting to have that many points if you assumed a flat histogram. So basically, let me give you another example so that you can probably relate a little bit more. If I have the first point as 1,000, okay? The first point as 1,000, okay? Using the same assumption. Where should that be? Where that new histogram, after histogram equalization, where should that be? The new level for 0 will be what? Again, each level should have 10. So basically, if I have 0 to 1,000, the levels, each level should have 10. Okay, if I have 1,000 in one level, I cannot divide that. I cannot have for 0, I cannot have a part of it as 0 and a part as 1 and a part as 2. No, it has to be mapped the same way. So basically, in order for you to get 1,000 points, you have to be at least at 100, right? So basically, you put the 1,000 here at 100, and so on. If you have here 50, after 10, this comes out like 50, 50 also will come, if I have new 50 points, I will reach 50 points after what? After 5 points. So basically, this is here at 10. Okay, I'll put here at 10. At 15, okay, I'll put the 50. Because basically, it had to accumulate that 50 from these levels. So these levels will remain flat and basically 0. And basically, I'm going to have that 50 over there. So basically, I keep doing that. As what I do is basically spacing out these values so that basically they fill out the whole range. And if you take the average, of all of these, for example, this 100 over 10, the average here will be exactly 10 like I used to have, like I wanted to have. Okay. Basically, we used to do that by hand, but now in Matlab it does that for you. But the thing that I wanted to be sure of, or basically to emphasize, is that the original 0 here became 10. Maybe I should draw it in a different color so that it becomes clear. Okay, 0 becomes 10 here. 0 level becomes 10. The 10 level becomes 15 now, because basically like exactly what I did here. Here, the 0 level became 1,000. So here you change the grayscale, you change the image values. When you do that, okay? For the image adjust, basically it does something a little bit different. Basically, if you look at the If you look at the display, if you look at the histogram that we had, let me show it again. It basically mapped it out throughout. So it looks exactly the same as the original histogram. But now it's mapped basically to the whole range of the display, and instead of being only in one very small part of it. Okay, like the one we just talked about here. Basically, maybe you can return to the original image. I think there is no redo here. It's no undo, because once we adjust the data, we cannot undo. But basically, the original histogram and the one after image adjust look similar. They have a little bit different values, but actually they look similar. Here, the histogram is very different from the one that we started with in the original image. Okay? So basically what you should do when you try to adjust the contrast for a particular image, use image adjust. What I would suggest is use image adjust and image histogram or equalization and see which one is better. And if none of them is good enough for you, then you should go and try the image tool manually so that you can get the quality of the image that you expect. Okay? Okay. Let's close these. Now we're going to talk about a different subject, a slightly different subject, about image filtration. Okay, image filtration is very important because basically, usually in images that you get from doctors, you usually have sometimes artifacts, and sometimes you have noise, and basically you use filters in order for you to do that, in order for you to improve the quality of the image. Okay. So basically, the image filter is just a system, basically. We talked about this topic actually a little bit more in 675, but actually here it's a little bit different. So basically, you have the input image and you have the output image, basically image dash, okay? And you have a filter here, okay? It's exactly the same system that we used to see before, okay? Sometimes this system can be linear. Sometimes you can use a nonlinear version or a nonlinear filter instead. You remember the difference between linear and nonlinear systems? What's the difference between linear and nonlinear? Okay, go ahead, Lo, if you have a question, if you have an answer.
Linear system is
Go ahead, continue. It maintains superposition. Superposition meaning that you have additivity
multiply
and you have scaling, right? It's related to multiplication, right? Okay, meaning that additivity, meaning that if you have x1 producing y1, okay, and x2 producing y2, then if it's additive, then you will have, if you have x1 plus x2 at the input, the output would be y1 plus y2. For the scaling, if you have x producing y from the system, if you have alpha x where alpha is a constant, you are going to end up with alpha y. Okay, so basically it's very similar. It's very simple actually. So usually if you have y as a function of x and only x, and you don't have x squared, you don't have for example square root of x, whatever, this will be linear. It's not going to be a problem. And basically the other important thing is that you don't have a constant. Okay, so for example, let me give you a couple of examples. Y is equal to dy by dx, or dx by dt. Okay, this is linear because actually x, as long as it's the derivative with respect to t, is still x. Okay, you consider it as if it's x. Okay, so if you have a linear equation, linear differential equation, this describes a linear system. On the other hand, if you have a nonlinear system, it means that you have something that has a nonlinear operation. For example, if I say that y is equal to maximum of x, is maximum a linear function? Is it a linear function? I don't think so. It's not a linear function, okay? Because basically it changes a lot of things. It doesn't have, basically it changes the position of x each time. So if you have a different x array, for example, sometimes the maximum is the first element, sometimes it's the second, sometimes it's the third. You never know, basically, okay? So basically it's a nonlinear operation. If you have y equals to x squared, x squared is a nonlinear operation, so it's a nonlinear system in this case. Usually, if you remember from your basic signals and systems, if you have a linear system, we're going to start with the simple case of a linear system. Linear systems, one of the main characteristics of linear system is that it's described by an h of s or small h of t. This is the transfer function but actually this is not just linear system, linear time invariant also, by the way. And the h of t is the impulse response. So you describe your system in terms of one of these. Let's just forget about the part about the transfer function, because we're going to talk about it when we talk about the Fourier transform and the image reconstruction, maybe the lecture after the holiday, inshallah. So we're going to talk about the impulse response. So if you have a system that has an input of x and an impulse response of h, okay, for example, basically the output y would be just the convolution of the two. Okay, so if you have this and that, if you have h of t defined for your system, so for any given input, you can compute the output. And the convolution, if you remember, it looks very similar. And basically, let's also take that to the discrete case. It's exactly, if you discretize that, you're going to have y of n is equal to x of n convolved with h of n. Very similar. If you remember the convolution theory, basically if you have an x that looks like this, sorry, okay, and you have, for example, h of t that looks like this. Okay, what you usually do is basically, this is x, and this is h of n. If you remember the convolution, we used to take that basically the original version of h of n and basically flip it. Basically, if this is 0, then I'll flip it with respect to 0. So basically, it becomes like this. Okay, and multiply this and this, and basically compute the output. I multiply this by this and add, and then compute the output. So here, for example, this is 1 and this is 2. Basically, just take the same values here. So 1 times 2 is going to be 2. So basically, the output here will be basically 2. Something that looks like this. Sorry. Okay, and basically, and then move it. I'll move it here. Move it by one element here. So basically, gonna be here and here. Now I have 1 times 2 1. So 1 times 2 plus 1 times 1 is equal to 3. There's gonna be something here. And then move it again. And so on. Basically, I compute the output y by just taking this operator or this h of n and basically flip it and shift it, and basically each time I multiply and add and compute the output at that particular position. Okay, maybe you didn't remember that, but actually it's exactly the same in images. So basically imagine that you have an image that looks like the following. Let me just outline a particular image. Sorry. Imagine that I have a kernel, a small h of n for the image would be two-dimensional instead of one-dimensional in the original case. So basically, you have values that look like this, okay? So you have here an image, and you have here h of n. This is h, and this is, let's just call it x, which is the original image, okay? Here you have n and m, because actually I have two dimensions, okay? Now I wanted to compute this convolved with this. What I do is do exactly the same as I did before. I just take this, and basically instead of having the basically apply it one dimensions like before, basically what I will do here is apply it in 2 dimensions. So basically I'm going to have that here. Just put the same exact one here, then move it by 1 here in this direction, okay, by 1. So basically the second time is going to be here. The third time will be here from this point here, from this point here, and so on. I'm also going to move it. And each time I'm going to multiply the values in the kernel, in the h of n and m, by the values in the image itself, and basically just add the summation, or basically add them together and just replace the value in the middle by this value. For example, if I take, if this image, for example, had values here of 7, 1, 5, 8, for example, here, and assume that the kernel had values of 1, minus 1, 1, minus 1, okay? If I put this kernel here, what will be the result or the filtered value of this particular position? I'm going to multiply 1 times 7 plus 1 times 5 plus 1 times minus 1 plus 8 times minus 1. Okay, what would be the value? 7 plus 5, 12, 12 minus 1, 11, 11 minus 8 is going to be 4. So basically the result from this position in the new image, in the output image, will be 4. So basically now I'm going to do that for each one of the pixels in the image and just get whatever basically the value out of this operation, and this will be the filtered image. This is called spatial domain filtering. Meaning that I define a kernel, this square with the values inside, I call it a kernel, The kernel is basically the impulse response of the two-dimensional filter. Okay, so basically I define that kernel and just use it to filter the image. Okay, so now in Matlab we have different ways of generating this kernel. There are several kernels that are well known, and basically you can just use them to apply certain functions to the image. Let me give you an example first. If I take a kernel that looks like this, what do you expect the outcome of the image to look like? Okay, let me give you an easier question. If I have a kernel, basically let's just assume that the values here, the squares here are the kernel. Basically, if I have a kernel that looks like this, 1, 1, 1, 1, 1, 1, 1, 1, 1. Basically, a kernel that is very simple, just all ones. If I use an image, if I have an image, my own image, okay, just assume that you have here an image, whatever image. Okay, if I convolve it with something that looks like this, what do you expect the output to be like?
The same.
It's not exactly going to be the same actually, because if you remember, this will actually be multiplied. This is going to be very small here. I'm just going to put it here and multiply these values by the points here. So I'm going to change the points definitely. But the change actually will have a certain effect. Okay, what that effect will be, let's try it experimentally first. Okay, let's take one of the images that we maybe you can just look at the image, exactly the same image that we just looked at. Okay, we'll go back and search for instead of Histogram, I'm going to search for image filter. There's a function called image filter. Okay, it's an n-dimensional image filter. Okay, so all you have to do is just have A as your image and H is your own filter. Okay, where do we come up with the filter? Where can we get the filter? Actually, it's very simple. Okay, so here what I'm going to do is maybe you can use one of the images we just started with. Maybe you can just use image, and basically I'm going to have H as ones of 3. Ones of 3 will generate exactly the same shape that we saw here. It's exactly like this. Ones of 3 will generate that. If you're not sure, ones of 3. This you can write it as 3 or just 3. When you just put one number, it's gonna assume that it's 3 by 3. So I'm going to use that as my H. And then I'm going to have image F, image filtered as image filter of image and H. And then I'm going to display that. Let's display it with the way that I showed you here, using image show with the other ones. But actually, we have a problem here, actually, in that the adjustments has to be used. So basically, let's adjust both, okay, just to be sure. So basically, I'm going to adjust the first and the second. So basically, I have image as we saw before. It didn't look well. Actually, it didn't look good when we use just image show. We had to use image adjust. So basically, I'm going to use image adjust for both the image before and after the filter. Okay, let's see what it looks like. Do you see a difference? I can see a difference.
Yeah, it's more like blurry.
Smoother, right? See here, that this part here is like a rough part. Here it
Sharp.
looks much smoother. Yes, it's not sharp. It's actually, as you said, it's blurred, but actually it's blurred is smoother basically.
Yeah.
In order for you to see something that looks really blurred, if you actually use a very large kernel, if you use, instead of using here a kernel of 3, let's use a kernel of 30. This will be a 30 by 30, and all of them are ones. Okay, let's try that. How do you like that? It's basically completely blurred out everything. Okay, so you can see much here. Okay, so basically it doesn't make sense, of course, to see something like this or use something like this. Let's use something a little bit larger, but actually not that much larger. 10. See, now the blurring is now very clear. It's very clear that when you try to basically reduce noise using a filter like this is basically a low-pass filter. Okay, and this low-pass filter, it actually reduced noise. Basically, if you see things here, it's much flatter. Basically, you don't see the kind of pattern that you see here. So you definitely reduce the noise, but at the same time, you reduce the resolution of the image. Because basically, if you imagine that you have an edge like the one here, okay, if you compute the new value of this edge by averaging a large area around it, then it's not going to be that clearly defined. The zero here, or the very low intensity here, will be blurred by the neighboring high-level values in the vicinity of its location. So basically, this is one filter. Okay, let's try other types of filters. Okay. Basically, there's a very nice function that is used by Matlab to generate filters that is called fspecial. Let's look at fspecial. Fspecial is the way Matlab uses to basically generate the different filters. It has several standard filters that are already there, and basically you can just use them. Basically, the first one here is the average is exactly the same as the one we used before. This is very similar to the just ones that we used before. Okay, it puts ones and basically computes at every point. It computes the average of its neighbors. Okay, and then uses that as the output of the filter. You can use it as, if you use average, is going to be basically a kernel that looks like a square. You can actually choose, instead of having a square, you can have it as a disk. So basically it looks like a circle. So that when you do the average, you do the average only for the point within that circle. Basically, in order for you to imagine that a little bit better, basically if I have a very large kernel, if I want to, for example, compute an image for this particular point, and basically the kernel is that large. 1, 2, 3, 4, 1, 2, 3, 4. Okay. Okay. So basically, you're averaging all these. It's a little bit, it's a little bit skewed, but it's fine. Basically, if you imagine that you're trying to compute the average of all these points, basically the neighborhood actually is defined by the distance. So the distance from this point to the edge here is different from this point to the edge here. This is a much larger one. So basically, if you have a circle, you're trying to basically include only the points that are within certain distance. So if you have a circle, if you exclude this part and include only this part, okay, then all the points will be less than this particular radius, which sometimes makes sense. But again, as I told you before, these kinds of options you have to actually try for yourself, because the implementation of a disk filter will be actually more expensive. If you try to implement it, it's probably going to be more expensive than the implementation of a square kernel. Okay, so basically you have to try this and that and see if there is a difference. Okay, but there are more. Basically, I'm not going to go through all of them, but I'm probably going to select the last two. Okay, basically there's something called Brewitt and something called Sobel. Okay, let's go and basically see what these look like. They look like this: 1, 1, 1, 0, minus 1, minus 1, minus 1. The other one here is 1, 2, 1. Yes? I have a question? Okay, that's fine. So basically, if you have ones and minus ones, let's focus on the Brewitt, the one that looks like this here. Let's try to see what comes out if I filter it with Brewitt. So basically, instead of having H here, what I'm going to do is I'm going to have H as F special of basically I can use it from here, Brewitt, and that's it. I don't have to even determine the size. But actually, it's a standard kernel. So let's see how that looks like, how the output from that looks like. How do you like that? How do you describe this output?
It's detect the edge of the.
Yes, it's the edge. It's exactly the edge. Why does it do that? Let's go back to the theory. Basically, if you have a Brewitt has basically, we talk about this particular filter. You have 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. Okay? So if you remember from the definition of the derivative, this is equal to what? Y of x plus delta x minus y of x over delta x. This is the definition of the derivative, basically. If you want to have the complete definition, you basically take the limit as delta x goes to 0, right? Okay? This is the definition of the derivative. This is actually the derivative in the continuous time. We cannot do continuous stuff on a computer. So basically, we have to approximate that in the discrete domain. So basically, in the discrete, you use exactly the same definition, but actually the minimum delta x you can have is 1. So it's going to come up like what? Y of, if you have, for example, n plus 1 minus y of n over 1 here. So basically, the derivative in the continuous domain becomes a difference in the discrete domain. Okay, so basically here what this does is, does what? It basically, for this point here, for the point in the middle, I'm taking this one here, just say, for example, this is 5, and this one here, this is 3, and making the difference between the two as the value of this point here. So if this 5 and this is 3, the outcome here will be 2. Okay, and this will be actually, because basically, if you look at the original image, if you go back and look at the original image, the edge is by definition defined as a difference in grayscale. So if you have, if this is an edge, okay, this is an edge, okay. Why this is an edge? Because basically the values here are like, for example, 10. All of them are 10. And all the values here are 0, for example. much less, this becomes an edge, because basically you're going to see a difference. You're going to see a step in the image between the 10 and the 0. Okay, so basically this becomes an edge. So inside, if you're talking about this inside, this is going to be 10, 11, whatever. It's going to be very close, right? And so on. And this is going to be 0, 0, 0, and so on. Okay, so basically, if you take the difference here, it's going to be 0. If you take the difference here, it's going to be 0. If you take the difference between these two, it's going to be 10 or minus 10. Depends on where the direction you have. And usually what you have is the absolute value of whatever comes out of this. So at the edge, you will have values, you'll have non-zero values. Basically inside, you're not going to have, basically going to have variation, but they are much smaller than what you would have at the edge. Basically, let's look at the edge again. See here, the points inside, they have differences, but they are very small. So basically, you see here some differences, but they are very small. At the edge, basically see, for example, this edge, this is very clear here. This is very different from this. You're going to see a very clear edge between these two parts. Okay, and the same thing here. You're going to see a very clear edge. The point is here is that since you have a kernel that looks like this, will it be able to detect a vertical edge? Let's think about it. So basically, this one here will actually be able to detect an edge that looks like this. But actually, if you have another one that looks a little bit different, for example, if you have 10, 10, 10, 10, 0, 0, 0, 0, okay, 10, 10, and so on, okay? If you have an edge that looks like this, basically, you're going to have a problem, because basically, along this edge, if you just take this kernel and multiply it here, you're not going to be able to detect differences here, because you're multiplying all of them by the same number. You're not differentiating between them. So basically, if you basically pass this kernel, wherever you have a vertical edge, you're not going to see much difference. And basically, if you look at the image that we have, the output that we have, you will see that all the vertical edges are not very clear. You can see basically that basically this is vertical, it's not very clear. Basically, this is horizontal, it's a little bit clear. Basically, any vertical edge is not going to be very clear with this particular kernel. Let's try something to basically use this exactly the same kernel and have another filter that is exactly the transpose. Remember the transpose? Transpose is basically, if you have a transpose of this, is going to be, if you basically, if I get the transpose, it's going to be basically 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. Okay, so this is the transpose. If this is H, this is H transpose. Okay, H transpose in Matlab is H dash. Okay, let's try and filter using H dash and see how it looks like. So here I'm going to have image F2 and basically filter it with H dash and basically take that and basically just display it as well. Image adjust of image F2. Okay, let's see that. See the difference now? See how the vertical edges are clearer now here? Okay, so basically, see here, for example, this wasn't even there. It didn't appear in the first one. So this is a map of the horizontal edges. This is a map of the vertical edges. How do you combine the two? If I wanted to get an image that has all edges.
Apply two filters.
Yes, but actually if you do that, if you take that and apply the filter, the filter is not going to look very good. Let's try it. Basically, I'm just going to say that this is, instead of image, I'm going to filter the filtered image with the new kernel. Actually, it looks very noisy, right? It looks kind of very noisy. And the edge here didn't appear. It wasn't there in the first place. So it cannot come out here. It didn't look very good, actually. So what you need to do is, basically, there are several ways actually of doing that. You can either, if you take the horizontal edge map, if I generated horizontal edge map, horizontal and vertical, you can either have the absolute value of both of them added together, or you can have actually consider them as this is actually representing the x-axis and the other one representing the y-axis value. So basically, if you want to take the get the whole vector, you can just get the magnitude of the vector. So basically, you can do both of them. You can just add them, just add the absolute values of both of them, or just add the squares and take the square root. Okay, let's try that and see how it looks like. So I'm going to add that here. Adjust of square root of Matlab is just QRT of image f square plus image f2 square. Square is just this symbol here. Is that correct? Is that correct? Actually, it's incorrect. Because we have a problem here is that we have matrix now. We have a two-dimensional matrix. When you have a square like this, it assumes that you're going to multiply image f by image f as a matrix multiplication. This is not what I want. I wanted to have element-wise power, basically. It's an element-wise operation. Whenever I wanted to have an element-wise operation, I have to add a dot before the operator here. So now it knows that instead of trying to multiply image f times image f as matrix multiplication, no, it basically applies this operation to each one of the elements that you have in your array. Okay? Basically, I'm trying to use different things in Matlab so that you can actually become familiar with that, and I hope that you can exercise them or use them during the assignment so that you can become familiar with them. Okay, missing argument, cell to function square root, cell to function, there's a problem, cell to function, not sure where the cell comes from. Image, okay, image adjust is, I wrote it incorrectly. Image adjust, hopefully it will work. Okay. Call to function square root. Square root. I'm not really sure why it's not working, but let me try and see this by itself. X is equal to this. Okay, let's get the help of square root. I'm not sure why square root is not. Square root is square root of the elements of x. Complex results are produced if x is not positive. It should be positive actually. Let's try and see how they look like. X here is unsigned integer. Oh, okay, sometimes there's a problem with integers when you're trying to use them in double or floating point operation like square root. So what I'm going to do is to have double of that. Double converts the data into double format. Okay, it worked. So just a matter of conversion here. Double converts the integer data into floating point data. So obviously square root is a function that requires the input to be double or at least floating point. So I'm just going to do it like this. Okay. Okay. It didn't look like anything at all, actually. I'm not sure why, but there's something wrong. Yes.
I suggest to take the square root of the filter of each one alone, doctor, before
actually you don't need to do that, but actually let's try the simple part first. Let's try the absolute value. Okay, absolute value of double of all of them, double of IM1 plus the same thing here, absolute value. We're just going to take the absolute values of the two and add them together. Which adjusts. Okay, there's another one here. Okay, let's show. That's right. Adjust. So basically, I just added them together, add the absolute values together. Okay. Integers of the same class. Okay, the integer issue. Maybe I should just put that as double. Okay. I hope it works. Double of this, and this absolute of double of this. Maybe this is missing here. Okay, that's the right way. The absolute value. This is the image address. It should work. Okay, still doesn't look very good. I'm not sure why actually. Image adjusts. It should actually be adjusted. Image F. Okay, let me try something different. It's very strange actually. It doesn't look very good. Image F. Okay, let's adjust it. Actually, it looks good. I'm not sure why it didn't work on the other one. See, now you have all the edges. Just compare them to the ones that you had before. Basically, compare this to this. Here you have the vertical edge, it's already there. But you don't have the edge here. The edge that was here, it was clear here. Actually, it's here. So basically, you see now both the edges in the vertical and horizontal directions. So actually, this should work. I'm going to adjust that code on the other code. Maybe I can just copy it. Just place it here so that it works. Okay, let's try that and make sure that it works. See, it works like that. So basically for F special, there are so many different things like the average. There are actually something called Laplacian. Laplacian actually does something that is a little bit different. Basically, it's all dimensions derivative. So it discriminates the image from all the images around it. It looks like an 8 if you have a kernel like Laplacian. here 8 and -1s. How many -1s here? You have 8 of them, right? And you have an 8 here. If you put this on something that has a flat background, it's going to make that flat background become 0. Okay, so the Laplacian is designed to discriminate between flat backgrounds and areas where the background becomes a little bit different. So whenever you have a perturbation or changes within the texture, the Laplacian will give you something that makes sense or basically can be useful. Okay, so I think it's enough for today. I think we covered. Do you have any questions first? Do you have any questions about what we talked about today? So basically what we covered actually covered these parts over there. This one here, experiment with reading, the windowing, we already did that. The contrast enhancement, we did that. We gave a very brief introduction to the basic spatial domain filters. We talked about this, we didn't talk about this, nonlinear filters, we gave any things like that. We didn't talk about simulations. We tried some experiments using image filter and F special. We didn't do anything with so basically the nonlinear filtration techniques we did not talk about, basically we could not cover this time. Do you have any questions about any one of these items? What I'm going to do is I'm going to basically prepare an assignment. The assignment will sometimes will ask you to find an image. Sometimes it gives you a particular image to work on. And basically it's going to ask you to do things like what we did right now. I'm going to ask you, for example, to generate a map of the vertical edges of an image, or a map for the both vertical and horizontal basically edges of an image, or ask you to do an average filter like a noise reduction filter like the one we just did, like basically use something that looks like an average, because average removes noise. Okay, so basically I'm going to ask you to do things basically that are applications of these. The thing I want to emphasize is that the assignment is basically you're allowed to ask your friends, you're allowed to ask me. Okay, if you have any problem with the assignment, if you have anything that they didn't understand, please contact me. Okay, you can contact me by email, and basically if you want to have, if you have more details or something like that, we can arrange for another further meeting or something like that, so that we can discuss the things that you have problems with. Okay? Do you have any questions? So inshallah next week, next Wednesday, you're not going to have a lecture. You're going to have also, you're going to have a lecture the following week, and the deadline will be pushed back maybe 3 weeks because of the holiday, first of all, and because actually you're going to need at least another couple of weeks in order to cover the part about the frequency domain reconstruction, image reconstruction. Next time, inshallah, we're going to start with the nonlinear filters. You're going to find that they are very similar. If you had some experience with the linear filters, they are very similar in application, but they are actually very interesting. They have some interesting stuff that cannot be done with linear filters. And then we're going to use some simulations in order for us to be able to see the effect of the simulation, effect of the filtration, whether it's linear or nonlinear. And basically, of course, experiment a little bit with the nonlinear filters that are available in Matlab. Okay? If you don't have any questions, then we're done for today. Any questions? Okay. So I'll see you on Wednesday in 2 weeks, inshallah. Shukran. Assalamu alaikum.
Alaikum salam.